But one of the things that's so great for me about organizing this event is I get to pick keynote speakers based at least in part on people I really want to hear speak. And Mike is one of those people. Dr. Mike Aldred, our afternoon keynote speaker, is an electronics lead with Dyson Limited in the UK. You may know Dyson for their renowned vacuum cleaners, hand dryers, and fans, highly designed consumer products. And the 360i vacuum cleaner that Mike's going to talk about is very much in the spirit of the kinds of products that we've grown accustomed to seeing from Dyson. And what I think is so awesome about it is it really embodies everything that we're talking about when we say computer vision is transitioning from being an exotic, expensive niche technology to being a mainstream, practical technology that can be deployed at consumer price points and in consumer environments, in this case in homes. Not to say that it's easy to do, but it can be done. And Mike has, I think, a really compelling story about the journey that Dyson has taken over many years to develop this really groundbreaking product, which its whole sort of differentiation is based on embedded vision. So I'm really excited to hear Mike's presentation. I hope you enjoy it as much as I know I will. And with no further ado, please help me welcome Mike Aldred.
Thanks, Jeff. Okay. Oh, we're on. That's good. Thank you, Jeff. And thank you for inviting me to speak as well. I can actually say it's quite a privilege to speak to like minds for a change. It's nice to talk to a room full of engineers. So thank you very much for that. What am I going to talk to you guys about today? Today's about a conversation around bringing vision to the consumer. So I think before I start on that, I'll introduce myself. Who am I? So I started at Dyson 17 years ago, and I'm category lead for electronics and robotics at Dyson. So what does that mean? It means I'm responsible for delivering everything electronics to do with robotics at Dyson. So that's the software, the firmware, the hardware, the sensing systems, the algorithms. And it's important to realize that's about delivering them on time, to spec, and to cost. What am I going to talk about today? Well, most importantly, I want to just share some lessons from the 360i development process. It's been a long one. It's not always painless. In fact, sometimes I would go so far as to say quite painful. And I just want to share some of the things that we've learned along the way. It's very focused around 360i, so there's a definite robotics bias to it. But it's primarily about the development cycle of a highly complex system, which has vision at its core. So I hope that it's relevant to all of you in some way or another, and that you can take some small nuggets here and there out of it. What it isn't is going to be full of maths and equations, and it's also not going to have any Dyson secrets revealed. So any competitors in the audience, apologies, you've wasted your time. Dyson. So just a bit potted history. What are we? So we're a domestic appliance manufacturer. We produce 8 million products a year, and we sell in 72 countries worldwide. The company was set up by Sir James Dyson in 1993. He still owns the product. He still owns the company. He's in there day by day, and he's still hands-on. He prides himself on being an engineer first. And I think you'll see as I go through this talk, that comes out in the way that the company's run. And I recognize that I'm in a very privileged position of working for a man who understands engineering. Talking about Dyson products, what are there? Well, if a product's going to sell for Dyson, it needs to meet a certain set of criteria. Firstly, it needs to solve a real problem. Okay? We start with a customer, and we start with a customer need. So we identify something that we have to solve, whether that be making vacuum cleaning simpler, easier, and better, or in the case of the robot, making sure that we can free up the user. We also set ourselves the challenge of being different and being better. So as a company, we'd never produce a me too product. We'll always aim to be better than anything else when we produce. And we need to be different. Innovation is absolutely at our core. Every day we are challenged to innovate and make sure we produce interesting and exciting products. And that means that we have to do things differently. Now, I'm an engineer, so I love turning up to work and I love being challenged. I've just realized I've actually said there were no equations, and there's an equation there, so apologies for that. The key thing for us is I want to be challenged every day. If I turned up to work and I knew what problem I was solving, I think I'd be bored. I think I'd struggle in that job straight away. So for me, innovation is about challenging yourself and challenging your team and making sure you strive to do things better. Throughout this presentation, I'm going to try and give a bit of a chronology of the actual product development. So from time to time, what you'll see are timelines such as these. So starting off, I started at Dyson in 1998. So I was doing a PhD in robotics, and my supervisor, Dr. David Bissett, was approached by Dyson, who wanted to start a robotic vacuum cleaner project. And thankfully, he said, well, I've got a team ready-made. So he picked us up and moved us to Malmesbury, which was quite a culture shock, because for those of you who aren't aware, Malmesbury is a very, very small village in the middle of the Wiltshire countryside. So it was quite a culture shock, but it's a fantastic place to work. In 2001, we produced DC06. So DC06 was our first robot vacuum cleaner. It had a PR launch, but it went no further. And it didn't go any further for one reason: it wasn't ready. It wasn't quite right. Cleaning-wise, it didn't do quite what we needed in terms of the performance of the machine being methodical. It was also quite expensive. It was a bit too heavy and difficult to manufacture. So James did what James does. He said, fine, it's not right, it doesn't go out. Learn the lessons, move on. So we went on to the next product. Now, just to give you an illustration, at that point in time, just to give you a sort of flavor of where we were, the best-selling mobile phone at the time was the Nokia 3310. Okay? Certainly didn't have a camera on it. Some would argue barely had a phone on it. And realistically, the biggest selling, and I really am not joking on this, I looked on Wikipedia, one of the biggest selling points of that was it had illuminated buttons. Okay, so that gives you an illustration of what mass market electronics was at that point in time. Okay, that was the best selling mobile phone. We then went on to another project, which unfortunately I can't tell you about because we did some stuff that we're going to use again later. And again, we got to a point where we'd learned a lot more lessons, and we had a fantastic product, but we decided again it wasn't quite right. So we went back to the drawing board. So the main thrust of the presentation today is actually going to start in and around 2005, which brings me on to 360i. So for those of you who aren't aware of the product, I'll leave you to a quick presentation if I can, please.
So this is the new Dyson 360i robot vacuum cleaner. The problem with existing robot vacuum cleaners is that they have very poor suction, so they don't make very good vacuum cleaners. We've developed a high-speed digital motor, which combined with the powerful cyclones, gives us very powerful suction. In fact, it's the first robot vacuum capable of high-performance cleaning. But crucially, it has this 360-degree vision system, so that it can see all the way around. This means that it can see where it's been and it can see where it's going, so that it navigates properly. It has a motorized brush bar which spans the full width, with stiff bristles to remove ground-in dirt from carpets and soft carbon fiber filaments to remove fine dust from hard floors. It's the only robot with continuous tank tracks. This means that it maintains speed and direction across all floor surfaces. We're bringing together all this technology that makes an intelligent robot that cleans your home properly.
So what I want to do now is go into the development cycle of 360i. And I'm going to break that into two logical sections. So the first one is about idea generation, and the second one is about product development. And those are two distinct phases at Dyson. So the first one is about basically building a scientific framework, and a knowledge base onto which you can actually develop a product. And separating them is critical because in the first part, you need a different mindset to the second. So let's start with the first one, idea generation. So this is all about thinking differently. When we start the product, we need to be broad-minded. We need to challenge received wisdom. And as we say there, try something that can obviously never work. James had a great quote, which was, be obtuse. Always be obtuse because there are 5 billion people out there who are thinking on the train tracks that they've been taught to think along. Okay? If you want to innovate, you have to challenge yourself, and that means really thinking outside the box. So with respect to 360i, what does that mean? Well, we set ourselves, and bear in mind, illuminated buttons on the mobile phone, we set ourselves the challenge of producing a vacuum cleaner that was better than a human. Okay, so in terms of cleaning performance, it had to have fantastic cleaning performance, but it had to be a vacuum cleaner first and a robot second, not the other way around. Okay, for us, it's all about the product. So vacuum cleaning is what we do. Vacuum cleaning is what the customer wants, so the vacuum cleaner is the king. The other aspect is we wanted to free up the user. The robotic aspect to all of this is you don't want to be doing it yourself. It's supposed to be freeing you up to do other things. And then the final thing was about not having to engineer the environment. So we didn't like the idea of having to put markers down or engineer your home in some way. You should be able to pick the machine up, put it down, and it should work. I quite like this illustration because actually I can attest to this one. My wife will tell you I'm the stereotypical man who really cannot do more than one task at once. So I have small children and I love my family time. When I'm vacuuming, I'd rather be spending time with my children. Equally, when I'm vacuuming, I'm thinking about what I should be doing with my children and probably doing a bad job of the vacuuming. Okay? So I think this is quite a nice illustration, the image of probably the mindset that I'm in. I'm not really concentrating what I'm doing because I'd rather be doing something else. So there's a real opportunity there for robotics to do something different. So we set ourselves our challenge. Why did we use vision? Well, actually this is one of the key points, and this is a bit robot specific, but it's very much related to vision. Product first. It's got to be a fantastic vacuum cleaner. What does a fantastic vacuum cleaner need? Suction, good pickup, good separation. What do they all need? Power. So our system is incredibly power hungry, which means realistically, we can't run for hours at a time. So 360i can run for 45 minutes before it runs out of battery. What does that mean? It means as a product, it's got to be very clever and intelligent about how it uses that energy. And that basically means it's got to be methodical. Okay, we can't move around randomly. Going over the same area floor 5 times is not a good use of your energy, okay? Especially as you've cleaned it the first time. So what the robot actually needed to do was know where it was. Now at the time, there were a number of technologies around that could have enabled us to do that. There's lasers, ultrasonics, infrared, but we saw vision as the key enabling technology that we should actually invest in. And there's a number of reasons. It provides a richness of quality of information. I have to say, I was nearly asking Jeff for his slide from his initial talk this morning, because I think it summed it up very eloquently. But the dynamism, the information content, everything about vision says it's the right technology to use. But it's not only the right technology for us for 360i, we saw it as the right technology for us to use because we're invested in robotics going forward. 360i is our first robotic product. We're already well engaged on our second and third ones. And we want to produce robots with far more functionality for the user. Now, if you're going to do those additional functions, the key thing is you need to understand the environment in which you're operating and with which you're interacting. Now, whilst lasers and to a certain extent things like ultrasonics can give you information that enable you to not bump into things and roughly work out where you are, they're not going to give you the information content about your environment to do those additional functions. Now, we also recognize vision is incredibly difficult. We knew as a company who, bearing in mind when I joined, the electronics in the product was a switch, a loom, and a motor, we knew we were going to be on a very steep learning curve. And we knew that vision was somewhere that we wanted to go down. So we decided it was important to get on that learning curve early and get ahead of the game, because only that way would we be able to stay ahead of the game. So it was quite a commitment at that point in time. So where are we? So we're now at 2005. Again, still no mobile phone cameras at this point, although we are beginning to get into slightly more interested embedded processors. So what we then went down was looking at using SLAM. So why do you need SLAM? So a question that's commonly asked is, surely you've got wheels, you know where you've moved. But actually, on a robot, things lie, and you've got to deal with the lies. So if I want to make a robot move forward 1 meter, I ask the wheels to move forward however many counts equate to 1 meter. And obviously, it moves there. Realistically, though, floor surfaces differ, and you get slip. Now, we also wanted to make sure we had a vacuum cleaner that could work on any floor surface: carpets, hard floor, flagstones, tiles, anything. And the amount of variable slip you can have is quite significant. So on carpet, you can actually achieve up to 70% slip. So you think you've moved 1 meter, and actually you've only moved 30 centimeters. Even worse, one wheel can have 70% slip, the other can have 50% slip. So actually, you've now performed a curve. And realistically, where you thought the robot was is nowhere near where it was. Now, bear in mind what we're trying to achieve here is a machine that's methodical and knows where it is. Only if it has those capabilities will you actually be able to use your energy efficiently, and other things like being able to get back to your dock to recharge and then carry on. So it's important that we can overcome this problem. At the time, Andrew Davison at Imperial College, actually he started at Oxford but had just moved to Imperial College, has started developing a technology called monoslam. Now, apologies, I know that some of the people in the audience know what SLAM is, but for those of you that don't, think of it very simply like a sailor used to navigate by the stars. So you use features in your environment, you look at where they are, and you use those to triangulate yourself. But the really clever part about SLAM is you don't start with a map. So you start with a blank sheet of paper. You've got to not only identify where those stars are, but at the same time, you've got to then use those to localize yourself. Okay? We play the video. So what you'll see in this video is where the cutting edge technology was at that point in time. So they were using a simple webcam. So basically, the SLAM system uses features in a room. Now, when I say features, it's not things like tables and chairs. It's simply edges, straight lines, okay, corners, those kind of things. So what it will then do is estimate the position of those in three-dimensional space, and then use some fairly complex maths and filtering and a Kalman filter to basically estimate the robot position. So you've got two things going on: the back-end maths, and the front-end system, which is tracking and extracting features from the environment. Now, Dyson being Dyson, and as I said at the start, we like to challenge ourselves. We thought, nah, SLAM's not difficult enough. Why don't we make it more difficult and use panoramic vision as well? Now, as an interesting question there is, why did we use panoramic vision? Now, for those of you who don't recognize it, that's a light shade. And myself and one of my colleagues, Charles Collis, were actually sat at lunch one day, and we were discussing the problems with using a forward-facing camera. And we've been thinking about this for quite a while, in the extent that one of the biggest problems is, what you won't have seen on the previous video, was when they use SLAM currently, they were just stood in the middle of a room and effectively waved the camera around like that. What that meant is they always had good visibility of the features. They were moving in a fairly slow tracked motion, and it was still a very difficult and challenging task, but actually a different one to the one we were facing. As a vacuum cleaner, you want to get right up close to objects to get good cleaning against the edges. But if you've got your camera on the front of the machine and you go right up close to an object, you're now blind. Okay, you can't localize yourself because you visibly can't see. So what we actually thought was panoramic vision. And we had a moment of inspiration. In the canteen, it's lit by these lights. We actually thought, I wonder what happens if you turn that upside down and put a camera underneath it. And that is exactly what we did. We literally borrowed one of the lights from the canteen. We created a rig where we just turned it upside down, got a video camera, and looked like idiots trundling it around Dyson on a trolley. And then we took the images and we unraveled them, and we suddenly thought, this is great. Because when I'm right next to an object, I can't see forward, but I can see the whole of the rest of the room behind me. Okay? And the key thing is, the information content is so large, the chances of you actually being blinded are massively reduced. So with our panoramic system, you can see 360 degrees around the machine, so it can always see where it is. The other aspect is that we can see from horizontal to up to 45 degrees. Now again, SLAM is about features and being able to track features. But this is another important aspect about using vision in the real world. The real world is infinitely dynamic in terms of the number of vision images that it can throw up at you. So you're going to have to deal with a lot. And in any system like that, that usually requires redundancy. Okay? If you only have a few features, if you track one of those, or you make one calculation wrong, you can throw your whole system out of kilter. Whereas if you have a really rich set of features, you can afford to lose one or two of them, and it doesn't make a massive difference. So we chose to go from horizontal to 45 because that's where the features are. Effectively, what we're doing is we're looking at the walls, we're looking at the tables, we're looking at the chairs, we're looking at the pictures, the windows. There is such a wealth of information there that we can extract a very large feature set and ensure that actually we can deal with the fact that we are going to lose a few of those features, and some of them may not always be visible. But there's such a richness there. The other way of looking at it is, what would you get in the other part of the image sphere? So what would you get if you went from 45 degrees to vertical? You get the ceiling. Now actually in here, it wouldn't be too bad. This is quite a feature-full ceiling. But I challenge most people to go home this evening and just wander around looking straight up. Okay, there's not a lot up there, okay? And realistically, it's usually a light fitting and the corners of your room. And if you misidentify the position of some of those, you're very quickly going to get lost or confused. So that's why we chose where we chose. So these are two real images from a 360i. So the top one is actually taken in my house. At this point, I'll introduce my children. So on the right-hand side, the two little legs there are my 3-year-old. On the far left is my son at 5, and you can probably see just behind my daughter, that's me stood in the doorway. So apologies, it doesn't give you a great idea of scale because she's probably 2 foot, my son's 3 foot, and I'm just over 5 and a bit foot. But what you can see there is you get incredibly rich content. Okay, that's a fireplace in the middle. You can see a sofa. You can see the windows in the background, a television. There are lots of edges and corners in there, and this is what I'm saying about that particular visual aspect contains a lot of information for you to use. Even if you tracked only 50% of those features, there's enough there that you're not going to get lost. The lower image is an interesting one. So you see the chair just by my daughter's feet. That's when the robot's hard up against that chair. Now, if I only had a forward-facing camera, that actually takes up 120 degrees worth of field of view. Okay, so you can see what I'm saying about that whole central section there would render you absolutely blind if I just had a forward-facing camera. So that really brings home the benefits of panoramic vision. Okay, so at this point, we've probably now done enough about the idea generation. We've decided we're going to use vision. We've decided we're going to use panoramic vision, and we're going to use SLAM. So we really kept our minds broad. We'd had a look around. We'd spoken to lots of universities and companies. We'd set ourselves a serious challenge, but all with a view of producing that product. Now, I think one of the critical things here is we realized that at this point you need to actually move forward towards product development. So, where are we? Realistically, at this point, we spent about 4 years thinking about the ideas, thinking about what we were thinking we were going to do. So that's quite a long time. In fact, 4 years, for a lot of you, is probably longer than your entire product cycle. Okay? But that was how long it took us to actually think outside the box. Now, what I've presented to you are 3 ideas that we had and then followed through to take on. What I haven't shown you is the 3,000 ideas we had that we didn't. Okay? And what I really want to sort of press home here is I don't want people to go away thinking we hit on those ideas first off. That took 4 years to come up with those 3 ideas, and there were many, many, many ideas that we tried that failed. But as James would say, it's not a failure, it's just a lesson you've learned. Okay, so we're now in 2008. We're up to the iPhone 3G. So we're actually beginning to get to some interesting stuff. However, I will urge you to remember the iPhone 3G only had a 2-megapixel camera. It didn't have zoom. It didn't have autofocus. It didn't have any of those things. It was a fixed focus camera. So we're still in the world where realistically the technology is challenging for what was already out there. When you go into the product development cycle, why are you doing it? We're doing it for a very good reason, certainly in my world, which is we're here to produce products. Okay? Now, for me, that is an absolutely critical message. To be able to produce a product, the company needs to know when to commit resource, how much money to put into it. The development cycle is the most expensive cycle. So the idea generation phase is about identifying where you want to actually try things, but reducing risk. When you move into the product development cycle, what we're actually trying to do is say, I understand the risk enough that I can now commit to a timescale and a requirement spec. So what functions are we actually going to deliver? When are we going to deliver them? That enables the company then to allocate resource and start committing plans onto a roadmap. In our world, it's at this point that the product actually makes it onto a roadmap and the rest of the business start knowing about it and plan for how they're going to sell it and when they're going to sell it. A critical aspect of the product development stage is you have to retain that thought about the customer. Now, I don't want to offend anyone in here, but vision and robotics are fantastic things, but they are not products. They are only enabling technologies. And when you're designing a product, you shouldn't be thinking about the technology. You should be thinking about what the technology is providing to the customer. And that should be your sole focus. It's incredibly easy to start thinking to yourself, oh, wow, it'd be really cool if I, and go off on a tangent that's interesting about the technology. And as soon as you find yourself doing that, ask yourself one question. What is this providing to the customer? And if the answer is nothing, stop doing it. Okay? Interesting is not good enough. Once you're in product development, you've committed to a timescale, you've committed resource. You need to stay focused. So unless you are genuinely providing benefit to the customer, you shouldn't be doing it. So, how do we go about developing 360i? Well, let's start with the localization system. So the localization system effectively is SLAM, and that's how the robot knows where it is. Well, the way that the robot knows where it is effectively has 2 aspects to it. The first one is the visual front end, where the vision system tracks features and tells the SLAM system where it thinks the features are. And then the second half is the EKF, so the actual SLAM, the maths. So the first thing we want to do is actually take vision out of the equation, because actually vision has a lot of noise around it and is incredibly difficult to prove out. So we wanted to start from a very firm basis. So the firm basis we started on was actually to only prove out the mathematics. What we did was create a virtual environment where we actually placed all of the features in a perfect circle and then fed the maths where those features would be if they had a perfect vision system. Can we run the video? So what you'll see here is exactly this simulator. Now, this is the output of the SLAM system. So what you can see is the SLAM system basically identifying the positions of those features. You can see the ellipses, which is the amount of uncertainty around those features, decreasing. But also, the robot path is being predicted. Okay? Now, clearly on this one, we actually simulated a very simple pattern. But what this enabled us to do was show that if you had perfect visual input, that the back-end SLAM mathematics system was working. Okay? And we could show, by introducing artificial noise to some of those features, how tolerant it was to noise and how much noise it could actually accept in from the vision system. What you see at the bottom there is actually a simulated image, which you'll recognize in a minute when you actually have real images on there. but those are the artificial simulated features being tracked. Okay, so what we now had was a system where we had confidence that the mathematical back end was working. We now needed to concentrate on the visual front end. And this is where I come on to a message that you'll hear me repeat time and time again, and that's testing, real-world testing. So what we did was we got a machine, we got the optics from a real machine, and we drove it around using remote control in real people's environments. We had a ground truth system that also recorded the absolute position of the camera. What we then did was, in, again, a simulation, feed in those image streams into the SLAM system that we now knew worked, so we were confident if anything went wrong, it was to do with the front end, not the back end. We play the video. So what you'll see at the bottom is, oh, unfortunately it's, oh, there you go. You can see features being tracked. So the squares are actually highlighting corners and straight lines. You can see the ellipses around those features in the image, showing how much uncertainty the navigation system has around those images, those features, sorry. If you look at the map above, that's also the robot now actively trying to identify where those features occur in the real world. It's actually doing that in 3 dimensions, not 2 dimensions, but obviously for the sake of this visualization, we've left it in 2. And then critically, it's now predicting the robot path. Now what you'll see here is that path isn't quite as pristine and crisp as the one you saw previously. That's because this is now using real-world data. So what we could do is take the path that was actually estimated from this and then compare that to the ground truth path that we had when we were driving it around. In other words, we now know how accurate our navigation system is. That brings about other benefits. So what we can now do is we could play with the parameters of the SLAM system and play with the parameters of the tracking system and see whether they positively or negatively impacted the accuracy of the system. So it enabled us to do a certain amount of tuning offline of the system. However, what is key there is that's only as good as the data set you're using. So just one quick warning there. Within about 2 years, we thought we'd cracked it. And we ran the machine around, and it was doing a fantastic job in my house and in a lot of the developers' houses. And I took it home to my mum. Mum, watch this, brilliant. And it failed horribly. And it failed horribly for one reason. We tuned it perfectly to homes in Malmesbury, and my mum's home is not representative of a home in Malmesbury. Our image data set was too small, and we'd effectively tuned a system to work in the limited number of homes we tested. And that was our first bitter lesson in the need to have extensive test and data sets. Okay? Now, it didn't actually take much to improve it to get to working in my parents' house, but the key thing is we hadn't realized how essential it was to have that breadth of testing. So at this point, we now have a localization system that we know how it works and how tolerant it is, but we needed to develop the rest of the robot. And by that I mean the cleaning patterns, the obstacle avoidance, the user interface, all of those kind of things. So what we then created was another simulator. Now this simulator didn't actually use the navigation system and the localization system from the first 2. What we did was create a black box, and we modeled it based on all the information that we'd found from the previous 2. So we now knew how much noise it had, how accurate it was, when it failed, if it failed, what the occurrences of those failures were. And so we modeled those into a system and used that to feed a simulator, which can actually then simulate the rest of the machine. Can you play the slide? So what you'll see here now is a robot, again, with simulated images, this time at the top. But it's on this rig that the developers actually test the behaviors of the machine. So this is the test of the cleaning pattern. Again, what we did here was we actually got a LiDAR rig on a little trolley and pushed that around people's homes. So again, that's actually my front room. So it's real-world data viewed from 10 centimeters off the floor, which is what the robot can see, and it enabled us to test how the robot's actually going to perform. However, a note of caution. Simulation is a fantastic tool, but it's only as good as the effort you put into it. I think Rodney Brooks said it perfectly when he said simulation is doomed to succeed. Now, the critical thing here is when you start, you do not know what is going to break your system. So your simulator is only going to contain the things you know about. A simulator needs to be continually developed. As you learn things in the real world, you need to fold those back into your simulator. Otherwise, you haven't learned the lessons. Okay, so simulation is only half the problem. Another small aspect to think about here is information optimization. That is actually the image directly as it comes off the camera on 360i on the top. It's only VGA, and in fact, we only use 480 by 480 pixels of that VGA image. So critically, once it's unraveled, you've now got 128K image there. It's not large. But what I would say is this: our machine can navigate. We only need to be able to navigate to provide exactly the function we want to provide to the user. So why would we do anything more than that? If I had a more powerful camera, or if I had color, or if I had greater detail, all I'd be doing is wasting effort and energy, because by definition, I can solve the problem with that. Okay? So once again, just because you can doesn't mean you should. So, testing. Testing and testing. We're now at the point where we're in that product development cycle. We actually started testing in real homes within actually just under a year of starting this project. So that's how critical it was to us. We didn't do runs around our lab. We didn't do simulation early. The first thing we did was go straight out into people's homes and capture images. Once we had a real representative rigs, and this is a robot-specific issue, we got into homes the second we got one of those. Because one of the critical things there is the embodiment of our vision system will by definition affect our vision system. You get vibration, you get noise. The placement of the camera on the product is all critical to your vision problems. It affects where you get lighting, where you get reflections, whether you get blurring, etc., etc. Vision is effective because it contains so much information. However, the critical thing is, for a mass market product, it needs to be robust and reliable, which presents a really serious challenge because you need to actually test in as many of those scenarios as possible. 640 by 480, 8-bit image effectively has 8 million different possible images created. If you now think that the robot looks at sequences of images, you're already in the billions in underneath a second as to the number of possible scenes it could have seen. Okay? Testing, 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 because you are not going to be doing it in theory. On 360i, we were actually testing for about 8 years. Actually, I know this is an underestimate. I think we're probably near 100,000 runs to actually develop our system and get to a point where we were confident it was robust. And we're still testing, even though we're going into production now. So what did we come across in the real world? As I sort of alluded to earlier, we like to go very close up to objects. Actually, that presented an unexpected problem. So you unfortunately didn't see it, but with the SLAM video, when they're tracking in the middle of a room, features move very simply and are very easy to track. As you approach an object, they move through the image very, very quickly. So they're very difficult to track. They have large search spaces when you're tracking them. So that required us to change the inherited way by which features were tracked and come up with our own way. Occlusion is another interesting problem. So slightly to the slightly to the right of the center line there, you can see a sort of black square. That's actually a bookcase. If I can get the video played, all I'll say is try and follow that black square. So it's continually disappearing behind the chair legs. And as you get closer to those chair legs change their look. And also, as you get closer to that bookplate, it changes the way it looks. Clutter and occlusion are very, very common in the real world. But actually, the SLAM system that had been developed in academia worked in beautiful open spaces a long way from the objects that they were looking at. So suddenly we were having to deal with the fact that we had feature sets that were continually going in and out of view and were changing the way they looked. And we got so close to that they were actually knowingly out of shot, even if we knew where they were. Image quality is another one. So the image at the bottom, if you imagine as illustrated on the left there, the robot's moving from a light room into a dark room. So the image on the bottom was taken in a light room. but looking into the dark room. So in the center of the image, you can see the dark room. And there are no visible features in that dark room, really. You can just about pick out the light, but actually within the room itself, there's nothing you could use. In the middle, it's actually now halfway between the two rooms. So at the two extremes of the image, that's the room behind, and it's now overexposed. There are a few features there, but not many. And the room in front is slightly better exposed, but not ideal. And then by the time you've got to the top image, you're now in the dark room, so you can see all the features, but behind you, the room is completely whited out. Now, this isn't specific to panoramic vision, but it is exacerbated by panoramic vision, which is because you can see all around you, you can effectively almost guarantee that you're going to have areas where there's low light and areas where there's lots of light. So what do you do about your exposure and gain control? Because realistically, you've got to try and pick your best one to get the best you can. So we went through a lot of cycles there. We started with, can we maximize the number of SLAM features? We went through to histogram equalization. Interestingly, what we actually ended up doing was just maximizing image entropy. Now, it's a very simple measure, and I think that's a key lesson. We started off thinking we would have to do something really complex and ended up doing probably the simplest measure, and that was the most effective. And it's not always the most complex things that come out on top to achieve a highly capable system. Sometimes trying the simplest things is best. And I think one of the lessons I've learned over the extent of 360i is actually I stop my engineers when they've come up with the simplest one and say, go and do that and see how it works before you think about what that might be wrong with it. Because it's very easy to come up with edge cases for any problem, but until you've actually assessed how well it really works, you shouldn't really progress because you don't know what you're up against. And many, many times, I've been in conversations where we've had wild, elaborate ideas, but when we've just implemented the simplest one, it's worked. And again, I come back to, if it works, stop there. Do the simplest things to achieve what you need to do and nothing more. Image quality, again, another aspect here. It's not particularly well illustrated by these images, but in the top image, the machine is actually stationary. In the bottom image, the machine is actually beginning to rotate. And actually, you can probably just about see by those stacked boxes on the right-hand side, it's blurred. Now, this is where robotics actually has a benefit over a lot of vision systems. It's in control of its own destiny. So this was in a dark room, and to get a decent set of images, you need to lengthen your exposure. The problem is, with a long exposure, if you then rotate fast, it's going to blur. So really beautifully simple answer here. We cap the robot speed based on the exposure time. So what you will actually see is if the robot goes into a dark area, it just slows down, and you don't get blurred images. So a really nice example of a closed-loop system where the robot is in control, and it's very, very simple. People in the real world will exercise your product. They will do things that you could never predict. So I've got 3 examples here. I promise you there's no cats on this one, though, which is the one that everyone usually expects. So on this top one, it's a bit difficult to see, but more or less in the middle of the image, you'll see someone coming out of the background there, if we can play it. So this is a very kind customer who comes out, and they have something in their hand, and it's a rug. And then they do that. Now, there's nothing we could do to continue operating in that environment. There's not a lot we can see. It's about educating the user. So there's a key point here. There are some things that customers won't necessarily find as obvious as people in the industry do. Okay? I found it very easy to go, really? And then actually someone pointed out to me that if you don't understand how a vision system works, it might not be obvious. There are customers, they're not wrong. So it's important that along with your product, you educate the customer into what you can and can't do. Actually, there's an aspect you can do there, which is, in that situation, when you identify that you've lost all your features, play dead. Users normally then get inquisitive about the product if you play dead. The second one, if we can run it through us for a little bit. Sorry, can we run the second one? So it seemed a bit strange. We had 2 features there that you can see that seem to follow the machine. So they move with the machine. The lighting changes. So we actually contacted the customer. Said, there's something a bit strange about your robot. We just need to know what's going on with this image. There seems to be something following the machine. She said, you mean the ears? And What had actually turned out is that when the product had got home, the kids loved the product, but it wasn't quite cute enough, so it needed some ears. And actually that's what you're seeing there, those are the 2 ears running on the machine. Just as an aside, it still ran perfectly. Okay, now that's not me encouraging you when you go out and buy your 360i to put ears on it, but that is another illustration of the robustness of the panoramic camera. The final image at the bottom is one that surprised even me. So my kids, I've been working on this product for 17 years now, so my kids have grown up knowing about robots and thinking it's entirely normal. What you're witnessing here is what I came in to find, and I said, Ollie, what are you doing? He said, oh, Daddy, I'm doing the robot dance. And basically, both of my kids think it's entirely normal to have a robot in the home, and therefore when they do dancing with the robot. Now, what it actually means is that quite often they interact with the machine, they sit on it, they poke it, they prod it. So as a test environment, it's fantastic at home because I've got 2 entirely unpredictable customers there. So, where are we? That's 2014. So in September, we launched in Japan. We've finished beta trials, and the product will go on sale there later this year. I'll answer it now because I know it will be a question everyone asks. It's on sale to the rest of the world early next year. Just in summary, and I think this is a really, really key message, we had 30% of our time spent on the product in that idea generation phase. In terms of extensive implementation, I think we only spent 10% of that time doing that. And then we spent 60% of our time doing iterations of testing, rework, redesign, testing, rework, redesign. If you'd have asked me what the balance of those were when we actually started the product, I think I'd have probably said 60, 10, 30. Okay, and I think that's a critical lesson there. I certainly did it, and I would lay a fair bet that the majority of people underestimate the length of the testing phase. It is absolutely critical to producing a robust, reliable, real-world product. Finally, just a comment from my boss. An inventor's path is chorused with groans, riddled with fist banging, and punctuated by head scratches. Stumbling upon the next great invention in an aha moment is a myth. It's only from learning from mistakes that progress is made. Thank you.
Fantastic presentation, Mike. Thank you so much. I'm sure there are dozens, if not hundreds of questions. We're only going to have time for maybe 2 or 3. I want to keep things on schedule, but Mike, fortunately, will be with us the rest of the day. He'll be available at the end-of-day reception, 5:30 to 7:30 in the showcase. Maybe, if we're lucky, he'll run the robot again, so you'll get to see it in action if you haven't already. So any questions for Mike? We'll take 1 or 2 now.
So, in addition to large rooms, I'm wondering about large houses. At some point, your SLAM is going to get, your environment's going to get too big. And have you tried using, do you only use the camera sensor to navigate?
Yep, so it is supplemented by an IMU. So we do have IMU in there as well. But basically, we only navigate by SLAM. We work in grids that are 5 meters by 5 meters. So the SLAM only needs to remain consistent within that 5-meter grid, and then it moves through portals effectively through each grid. So actually we can do expanded spaces. We have done plus 200-meter square spaces with no problem at all. The really nice aspect there is because the robot knows where it is, and it knows where the base station is, also battery isn't a problem. So it will run for 45 minutes, and at the point where it runs out of battery, goes back, charges, and then basically goes on and carries on where it left off once it's recharged. So effectively, we can continue expanding. The only problem we hit is memory space.
Okay, one last question for now. Go ahead, sir.
Hi, I'm very curious that why you chose Japan as a first market to introduce a product.
Okay, 2 very simple reasons. Japan is our second most successful market for vacuum cleaners, and Japan are absolutely robot crazy. So they're the right early adopters for a robot. They give incredible levels of feedback, and they're very enthusiastic about it, so they're quite forgiving. In fact, they went absolutely crazy for it. So it was definitely the right market.
Okay.
Quick question.
One last question. Go ahead.
Are you using global shutter? Are you using
Sorry, am I using?
global shutter for the camera?
Global shutter.
Oh, yes. Yeah.
Yeah.
So we basically, if you use a rolling shutter with a SLAM, you start getting into the temporal issues, especially on long exposures, as to whether a feature was taken at the same point in time. So yeah.
Great. So I'm afraid we're out of time for questions for the moment, but Mike will be around the rest of the day, so you'll have other opportunities to ask questions and hopefully see the robot in action. Once again, please join me in thanking Mike for the fantastic presentation.
Well done. Thank you.